Okay, let's take a look at f of -3.
Can you believe her?
Okay, so this stuff is not really related to our last unit, but it is going to be related to what we're doing in today's section, is kind of what we're going to discover here in these first couple of warm-up problems. Be careful, please, if you're dealing with exponents, especially on negative numbers, if you're plugging it into the calculator, you need to surround the negative number with parentheses before you do your exponent. If you don't, you will make a mistake. -3 to the 5th power is -243. Right? -3 to the 4th is a positive 81. If you don't use the parentheses, your calculator will tell you that was supposed to be negative, but it's not. 2 times -27. -6 times +9.
What did the con do?
Oh my god, you
My damn invalid list, dude.
how to do it. Like that little
You should have gotten 1086. I want to do number 2 as a synthetic division problem, but there is something that we should discover that actually makes number 1 easier, maybe an easier way to do number 1 while we're in the process of doing number 2. I do want to point out that we're using the same polynomial. Both of them use -4x to the 5th plus 3x to the 4th plus 2x to the 3rd minus 6x squared plus 5x minus 6. And when we're doing synthetic division, take the coefficients. Was I missing any? Do we need any placeholders of 0? I have a 5, a 4, a 3, a 2. That would be x to the 1. That'd be x to the 0. So no, we're not missing any. What number goes in the box? A -3. I want to remind you of the number that we plugged in on number 1. What number did we plug in on number 1? Oh, the same number that I'm putting on the box here. Let's look and see what happens. Sorry. That was supposed to be 123, not 6.
Yeah, you do. Like every day. No, did I hear that?
So when we divide this, we get our answer of -4x to the 4th plus 15x to the 3rd minus 43x squared plus 123x minus 364 plus 1086 over x plus 3. What do we notice that could help us with number 1? Look at the remainder. What was the remainder? The remainder was the same as the answer to number 1. So what we just discovered is that we can use synthetic division in place of substitution. We actually call it synthetic substitution. So this is evidence that the remainder theorem works. This is called the remainder theorem. So we are going to now transition from the warm-up into the section, but that's going to be known as the remainder theorem. So our next section is 5-6. Five six is titled The Remainder and Factor Theorems. The remainder and factor theorem. So the factor theorem I just showed you, or the remainder theorem I just showed you up above. But let's go ahead and apply it a couple more times. Oh, I didn't mean to say f of -1. It should say g of -1.
What's that one person iCarly that like puts in present?
All right, so let's go ahead and apply the remainder theorem to help us find g of -1. So I'm really setting this up like synthetic division. You'll notice I put some placeholders in there, some zeros in there, because there were missing terms. Started with x to the 5th, I would have expected an x to the 4th. There wasn't one, so I know it's really 0x to the 4th. So I have to include the 0 as a placeholder. Then I have x to the 3rd and x to the 2nd. I would expect an x, but I didn't have one. So that'd be a 0x, so there's another placeholder. And then finally my -1. Notice I did not switch signs. I'm doing g of -1. I put -1 in the box. I didn't switch signs. We switched signs up here when we actually did synthetic division. And when I gave a factor or something linear, I switched signs. This is unique. I didn't say x plus 1 or x minus 1. I just said g of -1. So you'll put the -1 in the box and then go ahead and do your synthetic process. Drop that first number straight down. Multiply it by the number in the box. Multiply it by the number in the box. 4 times -1 is -4. Combine them with the 0, you get -4. -1 times -4 is 4. What is g of -1? -6. We only need to look at the remainder. If you didn't get your zeros in there, it would not have worked. That is the answer. So, Jack, you asked me out in the hall if you had done that warm-up problem correctly. The reason I knew it immediately is because I looked at your remainder and I saw it was the answer of the first problem and I knew you did it right. So that's all we care about really, in this case, is the remainder, and that was a good way for me to check. You should have, yep. Let's do one more. I'm gonna change the instructions slightly. Oops.
I know what do you mean right now? Oh,
Did we have any missing terms here? Do we need any placeholders of 0? Look at the exponents. We have x to the third, x to the second, x constant. We have them all, so I don't need any zeros. So once again, if anybody's, I went through it quickly, but if anybody's questioning the process of synthetic division or synthetic substitution, first number gets dropped straight down. Once you get a number down below the line, you will multiply it by the number in the box, which was 4. So you'll multiply that by 4, which gives us the 8. That's what you'll write underneath the next coefficient. Then you add those together, -5 and 8 make 3. And then you just repeat that process. So that 3 gets multiplied by the number in the box. 3 times 4 gives us the 12. -1 and 12 makes 11. So then you multiply that by the number in the box, the 4. Giving you 44. Add that with the 14 and you've got your answer. Let's switch gears now. Enough of the remainder theorem. We're going to go into a division problem. Can I use synthetic division on this problem? I can. A reminder. Here's how you decide if it's a good synthetic division problem. You look at what you're dividing by, the x minus 3. What should be true of that in order for us to use synthetic division? What type of polynomial should it be? What type? What's the type of that? Should have a degree of 1 that's a type of linear, right? This is linear. Should have linear with a lead coefficient of 1. If you have that, it's a great problem for synthetic division. Mx plus b, so not x squared. Quadratic is if the degree is 2. If the degree is 3 is cubic. Degree of 4 was quartic. Degree of 1 is called linear. X plus a number, X minus a number. If you have that without a number in front of the X, it's perfect for synthetic division. So that's what I'm going to use here. It just told me to divide, and I can use synthetic division here. So if this is when I switch the sign. I didn't have to switch the sign on the synthetic substitution because it didn't give me something that was linear. It said f of 4. This is not f of 4. This is saying x minus 3. This is when I switch the sign. Coefficient. I was not missing any terms. Notice what I get for a remainder this time. We have a remainder of 0. We like remainders of 0. When you were doing division in elementary school, did you prefer to have a remainder of 0? Yeah, probably. Still, that's true to this day in any division. We like remainders of 0. In fact, we have a special name for things that you can divide that give you a remainder of 0. To help you think of that word, think about something pretty easy. 20, if you did 20 divided by 5, don't you get a remainder of 0? Yes, because you get a remainder of 0, we would then say that 5 is a blank of 20. What is that? Factor, yeah, 5 is a factor of 20 because you get a remainder of 0, it's a factor. Same thing is true here. Because the remainder is 0, I can say that x minus 3 is a factor of x cubed plus 4x squared minus 15x minus 18. If there was a remainder, it would not be a factor. But because the remainder is 0, we know that's a factor. We actually call this the factor theorem. Really, it's all it says is, hey, whoops, forgot a few letters there. That's your factor theorem. If the remainder is 0, you know you had a factor. So when the remainder is 0. So I'm going to now take a step, or kind of move into a slightly different version of this problem. Instead of saying divided by x minus 3, I'm going to say factor x cubed plus 4x squared minus 15x minus 18 completely. So we need to factor this completely. We just finished a section on factoring. So consider this problem. We're supposed to factor this problem. This problem has 4 terms. What's a strategy we can use to factor 4 term? Polynomials? Yeah, grouping. But does this problem work if you factor it by grouping? It doesn't work to factor this one by grouping. It does not work to factor this by grouping. No matter what, even if you reorganize it, it's not going to work to factor by grouping. So if we use the skills that we have right now, we would be saying, oh, it looks like it's not factorable. But is that true, that it's not factorable? We didn't we just prove that it is factorable? Didn't we already find a factor of it? Yeah, so it actually is factorable. I know one of the factors. I just found it. So let's write it down. So when I factor that out, what am I left with? When I factor out x minus 3, what's left? I'm left with x squared plus 7x plus 6 when I factor that out. How do I know that, and where did it come from? Remember your synthetic division up here? You got a remainder of 0, and in front of that is what was left. What's that? Yeah, yep. So we knew that was x squared plus 7x plus 6. Now, does that factor further? It says to factor completely. Can we factor that? Sorry, I'm trying to erase some of this stuff over here. Can we factor what's left?
That's the answer.
Yep.
I don't know why I did that, but I deposited ATM and then they got it. It's pretty good.
And then I can drive it all the way
Peter,
up.
if we can get that thing connected,
Have a party bus.
if you can connect that thing to your car, I want to see you drive it. Okay, well, we figure a way out. We've just seen it.
Like I was telling Robbie.
Let me erase some of this down there, but there's your next problem.
So will you be like given the factor usually?
For now, yes. So factor 3x cubed plus 10x squared minus x minus 12. Once again, that one is not factorable by grouping. Doesn't mean it doesn't factor. Instead, I gave you one of the factors. Right now, that's how it's going to work. We're going to give you one of the factors. When you get into pre-calculus, if you're taking pre-calculus, they won't be so nice to give you one of the factors. Instead, there's techniques where you can figure out what the possible factors are, and then you test them until you find one, and then you go from there. But for now, for this class, we will be giving you a factor. So what do I do? Yeah, divide it out. The factor is x minus 1, so the 0 was 1. That's what you put in the box. Yeah, it's AP. Oh, good, I got a 0. Did I expect to get a 0? Yes, either if we don't get a 0, one of two things happens. Either you made a mistake or the problem lied to you. Because this problem says x minus 1 is a factor. We know, because of the factor theorem, that we need to have a remainder of 0. So that just confirmed that that worked. So don't forget the x minus 1. I just factored it out. It still exists. It's just out front now. What's left? So we factored out x minus 1, and now I have 3x squared plus 13x plus 12. We have a quadratic. This is the type of problem we did in chapter 4. Some of you are better at that than others, maybe. But I did give you a problem where you have a lead coefficient in front of that x squared term. So this is the type of problem where we did a lot of practice using the x method. You'd put the a times the c up top and the b in the bottom. Your a is 3, your c is 12. You get 36 up top, 13 in the bottom. We need two numbers that multiply to 36 that add to 13. That'd be 4 and 9. So a reminder about what we do with that 4 and that 9, especially for those who aren't maybe that great at these factorings yet. What do we do with that? Some people are good at getting the 4 and 9, and then they don't know what to do from there. Here's what you do. We still have the 3x squared, but we don't have the 13x anymore. We're going to break that apart into a 4x and a 9x. Both are positive. The 4 and the 9 came from that x. And then we still have the 12. So the 3x squared and the 12x stay, but we split the 13 up into 4 and 9, 4x and 9x, based off of that x thing. And now I can factor by grouping. From the first grouping, 3x squared plus 4x, all I can pull out is an x, leaving me with the 3x plus 4. On the second grouping, I can factor out a 3. That's a positive 3. The positive there is probably helpful for in a little bit. Leaves us with 3x plus 4. Did it work? Are the two sets of parentheses the same? Yes. So 3x plus 4 is a factor. And what was left? X plus 3, that's a factor. And don't forget the x minus 1 that we pulled out right at the beginning. It's still there. Now it's factored completely. Just a heads up about, just a heads up, like a preview into where we're going in tomorrow's section. In tomorrow's section, we'll connect that to the graph. In tomorrow's section, we will connect this to a graph. Why are factors significant to a graph? What do the factors tell you? What do factors give you on a graph? Factors tell you your x-intercepts. If I had to graph that one, what would the x-intercepts be? The zeros? We'd have a 0 at positive 1. We have 1 at negative 3. What's the middle one going to make? What's that 3x plus 4 factor give us? Negative 4/3. Those would be our zeros. That's what we'll be doing tomorrow. Couple that with what we already know about end behavior. What's true of the right end of this? The right end goes up, and so you would go to the right of the rightmost 0, and we know it's going up. What's the left end going to do? Let's go down. It's odd degrees, so the left end's going the opposite direction. Boom. You can't hit the x-axis anywhere but those points, and we have a rough sketch of that graph. Largest exponent is 3x to the 3rd. So that's where we're going to go with it tomorrow, but there's really won't be much new instruction. It's just taking and putting that all together. So you don't have to worry about the graphing yet today, but you are going to get to the factoring.